Hey guys, this is OC. This is part of my series on guided notes, trying to help you guys out with some chemistry. And I try to do some of these important topics here. And today we're going to deal with significant figures, because it's a scary topic, and people are always worried about significant figures and what it means, what it does, and why do I actually even have to care. We want to take a look at it. Like, what is the purpose of a significant figure? So, for instance, like when I look at this diagram right here, where I have, I just got this, good old graduated cylinder. Okay, remember this is called the meniscus here, and I can see 7, I can see 6, I can see 8, things like that. So, like when I go down here and I see this is the bottom of the meniscus, what do I actually write down? Okay, and that's the problem for scientists. We want to know, like, seriously, when you write down a number, when I write down, a number like 5.72 milliliters, I is that the same thing as writing, 5.7200 milliliters? Well, I mean, if this is a drug and this drug is going to be administered to a patient and it's here to fight cancer or something like that, and I'm saying, well, as a doctor, I need you to administer this exact, and I shouldn't say use the word exact, but you need to use this amount of this drug. This drug is poisonous too, so if you use too much, it's a problem. These two numbers would mean totally different things to me. This one says, hey, I need to be accurate to all the way down here to the 100,000th place. Okay, whereas this one says I only need to be accurate to here. In fact, if I got 5.73, it wouldn't be a big deal, or 5.71, big deal. But if 5.73 is the amount that would kill this person, that's a problem. So in science, we want to be able to reproduce data in the same way. We want, we don't just want a number like 5. 5, you say 5 milliliters, okay? That's all well and good. However, what does that mean? Does that mean 6 milliliters is okay? 5.2 milliliters? What does that tell us? So significant figures is about how we look at measurements like this right here. Okay, so remember what you do is you look for your increments. So right now I know that this is a 7, okay, because this is 6, this is 8. My next notation, that's a 7. Okay, so what do I know here? I know these right here. I have 1, 2, 3, 4, and then the 7. So I don't know where the tens place is. The next tenth place is. I have markings to about, like, this right here is about 6.2, and this is about 6.6 milliliters. Okay, but those are, again, abouts. Because I don't know where 6.3 is. I don't know where 6.5 is. I don't, 6.5 somewhere in here. So I'm kind of, I know right now, if I look at this, I know I have 6 milliliters. Okay, because I'm above the 6. We are above this 6. I know I have 6 milliliters. Point. Now, what can I tell about this next place? And so that's kind of what we do in science. We sit here and say, well, I don't want to write more than I know, but I want to write what I know. I always say this in chemistry a lot. Number one rule of a chemist, be right. We're absolutely going to be right every time. That is an unflappable thing that we will do. We have to be right. However, rule number 2 is, after that, we want to be lazy. So I only want to write the numbers I need to write. So when I look at this 6, I know I'm above that, but I don't know where I am. I don't, that could be 6.6. That could be 6.7 if you look at it the right way. Maybe it's 6.65, and that would be 6.67. I'm not sure. So what this is a certain number. This one here, this is a certain number. Okay. Oh, sorry. Okay. Certain. We know this number. Okay. Without a doubt, we know that number is 6. Okay. So that's our certain. We have definite definitions. Markings for every individual unit of this area right here. Whereas if I go here, I don't know what this is. So I'm going to have to estimate this. Okay? And you guys know me. There's no such thing as guesstimating. Oh my gosh, I hate it. Okay? So we're going to estimate this digit right here. So I'm just going to estimate this to be, I'll think it's 6. Okay? If you wrote 6.7, that'd be fine. Again, this is a measurement, so you better have a unit. All right? Measurements always have a number and a unit. If you wrote 6.6, I don't know what you're talking about. 6.6, donkeys, dollars, people, children you like to beat. I don't know. Okay? So when you read these things, that's what you want to think about. Okay? If you look at this one, apply your logic to this idea too. Okay? What do you know? What don't you know? So if I look at this, what do I know? I know where 50, 60, I can see 40's marked. So if I think about the measurement value, I know the tens place. That's a certain. I know where every tens place is. Now, let's also see if I know where every singles place. So if this is my tens, okay, then what about my next place? Well, do I know where every individual unit is here? Here's 1, 2, 3, 4, 5, 6, 7, 8, and then 9. So, yeah, I do know where every individual single milliliter is. So I'm certain about that measurement because I have markings for every measurement of that. Decimal point, because I know that's my singles digit. What do I know about my tens place? My tenths place. This is tenths. What do I know about my tenths? Well, let's see. Uh-oh. Oh, no. I don't have any marks for tenths. But that doesn't mean I can't write anything because, we can imagine, little small markings in here, even though my pen right now doesn't let me do much of a nice division there. As humans, as scientists, we're okay with you estimating one digit. That's not a problem. That is a fair thing to do. So this will be my estimate, okay? And any measurement a chemist is going to write down is going to have always an estimate, okay? Always one estimate, just one though. No more than that. You technically can have numbers of, 50 certain figures in one estimate. You can have as low as no certains in an estimate, okay? So it's okay, but there's always at least an estimate. So what am I certain about here? Well, I know it's above 50 and below 60, so 5. What am I certain about here? Well, I know it's above the first line, second line, but below the third line. So I know it's 52, okay? And then the next part is estimate. This is where, as long as you're making a reasonable assumption here, you're not going to be wrong. I'm going to say 8. And then again, this is a measurement, so milliliters. Okay? So if you said 52.7, awesome. 52.6, bam, you're on the money. You're cooking with fire now. Okay? But if you wrote 51, that's a problem because 51 would be somewhere over here. Okay? That is not good because here, here's 51 right there. Okay, this is 52 here, and this is 53 here. Ooh, extra whole thing. Anyway, so that's how you record measurements. Okay, so when I'm looking at a number, how do I know what's significant and what's not? Well, it's easy, because you're not always looking at the measuring device. So you need to be able to look at just a number and tell, what does this tell me about the measuring device? Because that's when I look at a freaking number, that's what I do. When I look at a number and someone writes down 86 quatlus, okay? I don't know what a quatlu is. If you watch Futurama, maybe you'll know. But anyway, this is some measure value, let's say, okay? Well, I want to know, what do I know about the measuring device that measures quatlus? Okay. Well, according to me, something we've already figured out is that if you write down any number that's not 0, you're writing down a significant number. Okay. So I have 2 non-zero digits here. So this thing has 2 sig figs. Sig figs is like, our abbreviation for significant figures because, again, rule number 2, chemists want to be lazy. I'm still right saying sig fig, so hey, I can be lazy about it. But the problem is there's a number that sucks, and that number is 0. Because 0 can have 2 meanings. It can be measured, like you actually read it off the device. For instance, if you go back to here, what if this meniscus was right here? Well, then I'm trying to say that that's actually, hey, it's actually a 0. Okay, so I could have zeros that are measured zeros. I mean, there's nothing wrong with that idea. But there's also just ones where they're placeholding, and they don't mean anything. Their goal there is just to push our number out bigger or smaller. Okay, for instance, you go to your bank account, and you guys are rolling in the dough. You're rolling in the dough, so you look at your bank account. You got $22,000. You got more money than I'll ever have. $22,000. This is a measurement, so it's got a unit. American unit. That one goes in front. All right, so 22,000. Well, these zeros, really, in science world, those zeros are just placeholding because they're just pushing the 22 out there. I mean, you want your bank account to say 22,000. You don't want your bank account not to have those zeros, right? Yeah, you like that? If you like that, then I'll take the other 21,978 dollars that you don't want. So that is not representative of 22,000. So this freaking zero is a pain. Okay, so what do? There's some rules for zeros. Okay, and you can memorize all these rules. And in honors, I talk a lot about how to really think about the zero and whether it really is just placeholding. And placeholding means it's not significant, because it's just there for notation purposes. I mean, because I can't write 22,000 without them. They're just there they're there just to hold the place. I mean, they're not measured. But when I'm writing a number like 50, point 1, there's an example of a definite zero that's measured. I mean, there's no way to be certain about the 5 and estimating the 1 and not be certain about the 0. I mean, come on. I mean, you think about that measuring device. It has every tens of a milliliter or tens of a meter or tens of a gram, but and you're estimating the tenth of a gram, but somehow you know nothing about this place. Yeah, that's stupid. Okay, so these ones, the measured ones, are significant. Placeholders not significant. Okay, so here's the idea. If I write a number down, like if I look at a number that you write down, and you write down 11,000 millimeters, like that. Okay, in the science world, what we'd say is these are non-zeros, they count. Since these zeros are just here and there's no decimal place, we assume that these zeros that come after these non-zero digits, but they say before the decimal place, these aren't significant. All these zeros apparently are doing is pushing out these two ones out to the 10,000 and thousands place. So this sucker would only have 2 sig figs. Okay, that's it. All right. If you wrote the number though as like 11,000 point millimeters, you're saying an entirely different story. Again, chemists are lazy, so if I didn't want to write that point, I wouldn't. I mean, math people would be fine with this as doing math equations, But here in science, this means like something totally different to me. Now I'm trying to say that those two count, and the fact I wrote my point is I'm trying to say all of this counts. Okay, so this sucker has 5 sig figs. Okay, 5 sig figs. All right. You may wonder, well, how do I make it? What if the scientists wanted to express that these two zeros are significant? Okay, well, you'd have to go to scientific notation. Like if I said 1.100 times 10 to the 5th millimeters. Now, when I write scientific notation, I only write my significant figures. So those are the significant figures. This is an adjustment factor, no bearing on significant figures. So this is how I can get 4 sig figs out of that number. Okay? That's going to be important when we go to multiply and divide and all that good stuff. Okay? How about numbers smaller than that? How about like 0.00551 kilograms? Okay, well, here's what I'm thinking. If you think about this number, this zero, I mean, all I'm doing by that is notating I'm doing a decimal place, which, by the way, you should write the zero. Never write a number just 0.00551. The interesting stories about people who don't write zeros are found online everywhere, where rockets explode and crap like that, because idiots don't realize that, hey, it's very helpful to know that zero is preceding that decimal point. Anyway, so that zero is just there. It's like the nil zero. Like I haven't even measured anything there, zero. I mean, I've never even had 1 kilogram yet, so I haven't measured anything then. And if you think about it, if I haven't measured it yet, I know nothing about that decimal place. That must be just a placeholding. Okay? And again, I haven't measured this 0 either because I haven't even changed this decimal place yet. I haven't measured this either. Okay? There's been nothing measured here at all. Okay? You know, these zeros are just pushing out the 5, 5, and 1 out into the thousands, 10,000s, and 100,000s place. Okay? All right? So this sucker only has 3 sig figs. All right? These are placeholding zeros. They don't mean anything other than keeping the number out in its place. But significant figure-wise, only 3. Okay. What if I put a number, zeros after that? What if I had 0, 0, 5, 5, 1, 0? Well, see, now what I'm trying to say is, again, chemists are lazy. I wouldn't have written that freaking number if I didn't have to. Why did I write that 0? Well, I'm writing that 0 to say, hey, this is significant. Okay? So this is a 4 sig fig number. Okay? Because again, these aren't, if you think about an odometer on a car, I haven't even changed those yet. They haven't been changed. So they don't count for anything. Okay? So these sig figs are not sig figs. This one is a measured 0 because it's coming after non-zeros, and I'm actually going out of my way to write that 0. Okay? I didn't have to write the 0, so that's significant. That's another way to think about it. If I didn't have to write it, usually it must be significant if you think of it that way. Okay. And then finally, what about numbers like, what if I started out with 1.00551 cubic centimeters, let's say. Okay. Well, in this case now, this first part, well, I have a non-zero. That's definitely significant. No doubt. And if you think about, well, that's non-zero, that's significant. Non-zero, significant. Significant. And as we discussed before, in the last second, that must be significant too. But these zeros, are they significant now or not? Well, think about it again. Think about the measuring device this could have come from. Because that's where all these numbers come from. It's some sort of measuring device. Well, this device that measures this cubic centimeters, which would just be a graduated cylinder possibly, a burette, because cubic centimeter is a milliliter. I know that number. Again, if any number I write down is only going to have one estimate, and that's going to be the smallest number. So that's the estimate. So that means I'm also certain about all these. And I'm certain about this. So how could you be certain about this number, and then suddenly the device not have any other markings, but suddenly pick up in the thousands milliliter area, the 10,000s, 100,000s? It was suddenly certain in that realm, but not certain here? Get out of here. These are significant too. They're certain. So when you start with a number, a non-zero number, and then do decimal point and start writing other ones, whether this is 1.0051 or 1.00, these are, once you start with a number before the decimal and then start writing numbers after the decimal point, oh my gosh, they're significant. So this guy right here, we have this 1, these 2 zeros, there's 6 now because of 551 and that. This guy's got 7. This 100, 3. Okay? So that's significant figures. That is the idea. It's all back to thinking about, what does the device look like that I'm measuring with? Okay? If this is a device that has 1, 2, 3, and it's measuring, it looks like a graduated cylinder, but it's measuring, mardons. Okay? I don't know what the heck a mardon is. Metric system, who cares, I call it a mardon. I got kilomardons, millimardons. But anyway, and if this level is to there, then I know from this device, I can measure 1, I can measure 2, but I don't know anything in between, so I know it's 1 point. Now I'm estimating. So 6 mardons, Mars, let's say. Okay? And so now when someone writes down a number and someone says, okay, well, I have 2.78 Mars, I have no idea what the device looks like, but I know that they estimated this, and the device must have markings for 2 and 7. So it must have this single-digit marking and must have that marking. So that's what you want to think about every time you do sig figs, is the device, and it's a way for you to communicate, how good is this device? Is the device, like this, or is a device like this? It tells me a lot of good information about that. Okay? So that is the purpose and reason for significant figures. All right? All right. So now, what do I want to do if I want to do math with significant figures? So like, do I really care about that or anything? We do. And there's going to have to be some interesting kind of plays here. And I'd say I don't know if I have a perfect explanation for all these, but I can, add, subtract, I can explain usually well. I will say I'm going to actually do a video demonstration of this idea on YouTube, and I will link to that. So you can definitely take a look at that. I'm going to show you, the volume idea of add, subtract when we do a sig fig. So. But let me just go ahead and give you the basic paper and pencil idea of add, subtract, multiply, divide. So let's say somebody is adding two lengths together. And let's say Bob measures something at 4.64 meters. And Clyde, what a great name. Clyde uses a different measuring device, and he wants to add to this. Let's say that's the length of a steel beam they're building a building. And Clyde, he has a crappy measuring tape that day. And his measuring tape only measures out 3.1 meters. Okay? And they're going to weld these two bars together. Okay? So when we weld these two bars together, we want to add them together and know what our total length is now. All right? So when I add these together, I have 4.64 meters. All right, so I'm going to add these together and add 3.1 meters to this as well. All right. Now, when I add these together, what's my resulting answer? Okay. Well, in math world, this is easy. You weld them together, you add them up discretely here, so 7.74 meters. All right. In the science world, let's say, I don't think so, pal. This guy's measuring device was suckier than this one's. Okay? In fact, if you think about this number, he was certain about his 3 and he estimated that 1. And if you think about Bob, Bob was certain about his 4 and his 6 and estimated this 4. So if you think about this number here, this was an estimate. This was an estimate on Clyde's. So 4 in the resulting, when you think about the welded piece, are you sure it's 4? Because what did you know about this digit? Nothing. Clyde didn't have a good enough measuring device to tell you anything about that spot. He couldn't estimate. He couldn't even estimate it. Could be a 9 there, could be a 42, could be a 36. I'm just kidding. It can really only be a number between 0 and 9. But I don't know what it is. I just know nothing about it. Kind of a contradiction there. However, when we look at his tens place, he estimated the 1. Now, you were certain about this 6 in Bob. Bob was certain he had 6, but that could have been a 2 in Clyde's example. That could have been a 0. Could have been a 3. Maybe he just had a bad day or something like that. Maybe he had a rough night or something like that. So, do you really know that that's 7? I mean, if you're not sure that that's a 1, and you're adding that to a certain 6, are you sure, any more sure about this number than the fact that it was estimated? Not really. So this is estimated too. Now, both people were certain about their singles digit. So I'd say we could be relatively certain that that's a 7. Okay, if you're certain about both those numbers, that makes sense. Okay, but again, in science, now you got a problem. 2 estimates? I don't think so. So we can only keep our 1 estimate. So the basic rule you see in a lot of books is you start from the right and you go to your left and you keep the decimal place of your leftmost uncertain digit. Okay, it's kind of like the decimal place of the lesser estimation, aka the biggest decimal place with estimation. Well, that's the tens place in this case. All right. So what I'm going to do is I'm going to kind of a lot of people draw lines here, to say, sorry, my line sucks, to say, okay, I'm going to keep everything from this estimate and to its left. All right. And we would round with this, rounding, you can read the book about rounding, people have different theories on rounding, things like that. We're going to take a basic look at this, this is a 7, so should I round it up to 8 or keep it 7? Well, I'm going to let the 4 govern that. 4 is less than 5, so I'm going to keep that 7. So I should really change this answer to 7.7 meters. Okay, and so that's what this answer should be. All right. So when you're adding and subtracting with significant figures, and especially sig figs of different measured values that came from different setups, then you really need to think about, well, I can't have more estimates in my answer than what I'm putting together. Okay, All right, so and look at my video on YouTube. That'll make a little more sense. That'll help you kind of give a visual sense of why that works out that way. For multiplying and dividing, what do you do on that? I don't have a great explanation for why this is the way it is. However, here's the basic idea. This one kind of a lot of people love because it makes to them more sense. I think as subtract makes a lot of sense to me. However, let's talk about multiply divide. So let's go with Bob and Jen. Okay, Jen's measuring out. You're trying to find the surface area of a desk. So you can, wrap an aluminum foil for a prank on a friend, because you were thinking, oh, you want to get back at him for, punking you, like Ashton Kutcher. Oh, God, I hate that guy. Anyway, so you're going to, aluminum foil his whole house. So Jen and Bob got together and want to do this, and so they're trying to do this, trying to calculate surface area of this table. So Jen measures out, she brings her ruler that day, and she realizes that the width of this table is 38.49 centimeters. Okay, Bob is not good at all. Bob only figured out he brought a measuring device that only told him the length of the table to be 12. Oops, sorry, don't mean to have that decimal point there. 12 centimeters. Okay. So you want surface area. Well, surface area, that's easy. You multiply these two together to get centimeters squared. Okay, so you're just going to multiply these two. So I'm going to use my handy dandy calculator I have here. And so when I do 38.49 times 12, mathematically I come up with 461.88. Again, this is a calculated scientific value, so centimeter squared. Because centimeter times centimeter, centimeter squared. So you're like, oh, hey, look, there's my answer. And I'd say, well, Bob's number really wasn't that great. And technically, the number we have here is even better than Jen's number. Jen has 4 sig figs. Bob's got 2 sig figs. Okay? Add subtract, it's not about technically the number of sig figs. It's where your estimate lies. However, in multiply divide, we go with the idea of, well, you check the number of sig figs in each of your component numbers. This has 2 sig figs, this has 4. And since the chain is only as strong as its weakest link, the idea that if you have a chain, okay, if you have this chain here, that the chain is only as strong as its weakest link. So if this link sucks, when you pull on either side, it's going to break at the weakest link, all right? It's like when you want to keep a secret with friends. It's a friend who gabs the most is the one who's going to give it away. So what I want to do here is I have a 5 sig fig number. I can't have 5 sig figs when I only have 2 and 4 making up my component answer. So we have to get this to the lowest number of sig figs that we had to make this up. So I'm going to keep 2 sig figs. So I'm going to keep my largest number and my next to largest number, and that gives me 2 sig figs right there. So I'm going to call it a day at that. Again, I would round just like I did in the previous problem. Should I round 6 up to 7? Well, this is a 1, so no, I'm going to keep that for 460. So 460, no decimal point because that would make 3 sig figs, centimeter squared. All right, and I would do the same thing for division. All right, so add, subtract, keep your leftmost estimated digit and everything to the left of that. Multiply, divide. Go by number of sig figs in your components. The lower one is what you're going to have in your answer. Okay? All right. Let's do just one more, and we'll see how you guys do. All right? So let's just generate some numbers here. So let's say I had 18400 milliliters. Okay? And let's say I'm trying to find the density of an object. Okay, remember that's mass over volume. And let's say I use a balance, because balances and graduate cylinders, if we're using a graduate here, are going to have different, sig fig values. So you use my balance in the back, and my balance comes up and tells you that you have a mass here of 38.6221 grams. Okay. So you plug this in for your mass, plug this in for your volume, and let's see what the calculator says. Calculator says 38.6221 divided by 18400. We come up with a nice large number of 0.00972, and again, this is a measurement. We took grams and divided it by milliliters, and they don't cancel each other out, so it's just U over ml. That's great, I'm done, yay! Oh crap, there's no way this number can be that big. I mean, there's no way from these two numbers, that, in this case, here's an estimate number in this one, this is the estimate on this one. Again, remember, these zeros are placeholding, they are not significant, okay? So this is a 3 sig fig number, this is a 6 sig fig number. So what do I want to do here? What do I want to do here? Well, hundreds place is my estimate here. I wonder if that matters. Probably not. Oh, 10,000ths place here. Oh, right. The lowest number of sig figs in multiplying and dividing. So I have 6 and 3, so this one should have 3. Okay? Is that zero significant? Nope, it's placeholding. Is that zero significant? Nope, placeholding. Is that zero significant? Nope, placeholding. Is this 2 significant? Yep, non-zeros. So here we go. We're starting counting our significant figures. 1 sig fig, 2 sig figs, 3 sig figs. Okay? So I'm going to cut it off here. That'll give me my 3 that my lowest value had. All right? Now I want to round. So should I round this 9 up or not? Well, this is a 9, so heck yeah, I'm going to round up. So now I'm going to round that to 10, which is going to make this a 0. And that's going to add 1 to this digit here and do nothing here. So we have 0.00210 gram per milliliter. By the way, when you see this, these are the same thing. This is how you write it in one line. This is how you would write it if you have all the space in the world. So you see a lot of people in text write grams per milliliter like that, but they mean the same thing. So, all right, and that's the correct answer, obeying sig figs. All right. All right, I hope you found this helpful. If you need more help, please email me. My email's on the website, and you can contact me anytime. Thank you very much for watching. Have a good day.